Okay, so video 6 now on section 2.1, moving into chapter 2, all about functions. Most of chapter 2 will be about functions. So what are functions? Well, functions are things. They're sent over a lot of mathematics. When you're doing analysis, you want to use functions. They have a very nice property. And the idea of a function is that you have a bunch of numbers, which we'll call the domain, with the x values, and a rule. And the rule tells you, given an x value, what's the y value that goes with it, right? So running a number through a rule gives you the new number of the y value. And the collection of all possible y values is called the range. And the key point of an ask function is this. Each x value is assigned one and only one y value. If you know the x value, you can calculate the y value. This is called a number of different things. You probably know this statement as the vertical line test. Okay, so what's the idea behind a function here? Well, you have a pile of numbers. We call it the domain. And you have a rule of some sort. And that gives you out some new numbers, and we call that the range. So suppose you had in your domain the number 3, and that got assigned to the number 9. And suppose you also had in your domain the number 6, and that got assigned to, so we'll try to make that a little legible, 36. Right? Maybe we'll get a little fainter. You know, the 3 goes to 9, 6 goes to 36. So what's going on here? Suppose you take any number in a domain. What's the rule that associates it to something in the range? Well, you square it. Right? So y equals x squared. So that's a function. It takes certain numbers like 3 and 6, whatever number you want, and gives you back another number. If you give it 3, the rule says 9. If you give it 6, the rule says 36. If you give it any number x, the rule says y is x squared. You square the number. Okay. We can set up a different one, right? But the picture is always pretty much the same. There's a bunch of numbers in your domain. There's a rule that takes you to your numbers in your range. Right? And suppose this number now, you give it the number 9. And it gives you back the number 3. Or if you give it the number 36, and it gives you back the number 6. And you can imagine what would happen if you gave it the number 4. It would give you back the number 2. What rule are we talking about? Well, if you give a number x, it would give you the number y equals square root of x, right? So if you give the rule 9, the rule says 3. If you give the rule 36, the rule says 6. If you give the rule 4, the rule says 2. What does the rule do? It takes any number you give it, say x, and it gives you back square root of x. Of course, minus 2 is outside of the domain of square root of x, right? If you try to give minus 2 to the rule square root of x, the rule says, nope, not taking that. Minus 2 is not one of the numbers I look at. So it's outside of the domain. It's not part of the domain. Likewise, if you ask the rule, what kind of numbers do you give me? The rule will tell you, well, I only give you positive numbers. You give me a positive number, and I'll give you a positive number back. The rule will never give you minus 3. So the domain and the range might not be all numbers, right? The domain for square root doesn't include negative numbers, and the range for square root also doesn't include negative numbers. Note, incidentally, minus 3 is outside of the range of the squaring function too, right? If you take numbers and square them, you'll never get minus 3. So domain and range, they don't have to be everything, but sometimes they are. Okay, so moving on a little bit. There are many ways to depict functions, and in this course we'll focus on 3 ways to think about functions: tables, graphs, and formulas. There are others, but in this course in Math 196, tables, graphs, and formulas are what we're going to do. So functions and tables. So after we do this example, section 2.1, problems 11 through 14, you should be able to do that. X's, that's my domain. Y's, that's my range. So what's the domain of this function? Well, it's the numbers 1, 2, 5, 7, and 10. What is the range? Minus 1, 7, 4, and 3. So we can list that. Minus 1, 3, 4, and 7. Those are the numbers that occur in the range. The domain is 1, 2, 5, 7, and 10. Oops. And what's the rule that takes me from one to the other? Well, there really isn't a rule, right? All I know is these 1, 2, 3, 4, 5 pairs. And the rule is that 1 goes to -1, 2 goes to 7, 5 goes to 4, 7 also goes to 4, 10 goes to 3. So an important point to note, y's can be repeated. Apparently repeated can't be spelled though. Let's try that again. Y's can be repeated. You can have two different numbers, in this case 5 and 7, that both go, that give you 4 as an output. Oh, that's okay, that's no problem. The key is that each x equals 1, for example, gets exactly 1 y. X equals 2, that it gets exactly 1 y. Oh, so this is a function. Y, each x gets exactly 1 y. Each y can get more than 1 x, but that's okay. Okay, so example 2, right, here's a table. Looks like a function, is it? Well, what does our rule say? 5 goes to -3 or 5 goes to 3? Big question mark if you look at these two. And likewise for 4. There's a problem. Right? To be a function means that each number goes to exactly 1, each x goes to exactly 1 y. So here 4 goes to 6, or does 4 goes to 7? Can't tell. So, not a function. And we can't even say if there's a domain or a range, because those are things that functions have, and this isn't. Okay, so when we're looking at a table, each x has to appear just once in the table, although the y's can appear a number of times. But if there's more than one x in it, it's not a table. If a particular x value shows up more than once, then it's not a function. Okay, on to graphs. This is actually a little more important than tables. So sections 2.1, 2.2, 2.3, we'll be dealing with graphs a lot. So here's a graph. This is some function y equals f of x. I don't know exactly what the function is. I made it up at some point. What we want to know is y equals f of x. What is the domain? Well, actually the first thing we want to do is this a function? And then domain and range. So one of the questions is determining about whether or not it's a function is, how do you read a graph? How do you read this kind of graph? What is the rule? Because we don't have a formula or anything, or a table. And we need a rule that'll take us from our domains, our x's, to our range, which is our y's. So, oops, wrong one. I want a red pen. So, how do you read a graph? Well, there's x equals 2. Right? This is the x-axis, right? All along here. That's where my x's live. Right? That's where my domain is. So if x is 2, what's the corresponding y? Well, you start at 2, you go up or down until you get to the function. There's a point on the function. And then you slide over to the y-axis. And this is y equals, well, this is 10, this is 15, this is 20, so maybe y equals 12.5. So f of 2 equals about 12.5. If I put in x equal to 2, I get out the corresponding y, 12.5. How do I read a graph? You start on the x-axis, you go over to your y-axis. Right? So what about, say, f of minus 0.5? What y value to get out there? Well, there's my x, minus 0.5. Go up to the axis, to the graph, and then I go over to the y-axis. And so this is 5, so this is about 4, say. And again, reading this notation, this is the x value. I start on the x-axis, right, my domain. Oops, what's my y here? My y is 4. And that's my y value. And that's on the y-axis. Great. So, is this a function now? We can ask that question. Oh, I just need to get my black pen back. Is this a function? Well, what does it mean to be a function? We'll go all the way back up to the top. Each x value is assigned one and only one y value. So, what's the rule for a graph? Well, you start at some point on the x-axis, you go to the y-axis, you go to the graph, and then you go to the y-axis. So the rule for a graph, start on the x-axis, go up or down to graph, and then go left or right to the y-axis. Now, given this graph, if I pick any x value, we'll scroll back down. Right, if I pick any x value, and I go up or down till I get to the graph. So if I start here, here's the graph, and then I go over to the y-axis. Right? Is there any x value where if I go up or down to the graph that I hit the graph twice? The answer is no. Each point on the x-axis has one point on the graph above it or below it. It passes what's called the vertical line test, because if I put a particular x value, and I put the vertical line through that x value, I only hit the graph in one point. So, is this a function? Yes. It passes the vertical line test. Right. Each x gets exactly one y. If we look at this graph, however, is this a function? The answer is no. Why not? Well, the rule for a graph is you start somewhere on the x-axis, say at minus 0.5, and you go to the graph. Here, I can go up to the graph, or I can go down to the graph. So this must be, if this is 0.5, this is, say, 0.8, and this is, say, minus 1.25. So if x equals minus 1/2, that's this point, what is y? Well, it's either 0.8, this y value, because we went to this point on the graph, or minus 1.25, which is this y value, because we went to this point on the graph from there. Functions don't do ambiguity. No ambiguity for a function. And we'll put a little exclamation point. It can't be either this or that. It has to be exactly and only one thing. Right? And so when you look at this and say, well, it could be 0.8, it could be 1 minus 1.25. Well, we can't have that. There has to be exactly one y value, and x equals minus 1/2 has two possible y values. Of course, not all x values have exactly one y, more than one y value. Right? If we take x equals minus 1.5, there's only one point on the graph above it. It counts to 1.5. But, that doesn't really matter. All we need is one x value that's got more than one possible y value to make it not a function. So this is not a function because there's just too many options for x equals minus 1/2. So this does not pass the vertical line test. A vertical line through x equals 1/2 hits the graph in 2 points. Oops. Having issues there. There we go. So this graph fails the vertical line test. Period. Okay. So we can tell if we have a table or if we have a graph whether or not something is a function, right? Functions as formulas. So problems 55 through 60 in section 1.2. Oh, here we go. Just figuring out where my notes are. So y equals f of x. You may have seen this notation, right? F of x is usually given as some kind of a formula. We're only dealing with certain types of functions here. Some polynomials. We'll deal with exponentials and logarithms later in chapter 2. Lines, absolute values, square root. So when you have a formula, the rule that we have is plug in some number for x, do whatever calculations the formula says, and see what you get for y. Pretty straightforward. Finding the domain and range of functions from the formula, that can be tricky. Also, telling whether or not something is a function, if it's actually expressed as a formula, it's pretty much always a function because it's y equals some function of x, right? And so you plug in the number for x and you do the calculations, and there's only one possible outcome for y. Ranges, there's really no useful rule. You have to graph the function really to figure out what the range is, but there are some useful rules for domains, and these are the 3 rules about domains of functions. And remember that the domain is the numbers that you can plug into the formula. So for us, in our class, given the functions that we're going to deal with, the domain of any function is all reals, and there are 3 exceptions, so except for 3 exceptions. 1, if a function is defined as a fraction, the denominator can't be 0. 2, square roots and other even roots like 4th roots or 6th roots or 8th roots, they can't have negative numbers inside of them. You can't take the square root of minus 1, for example. You can take the cube root of minus 1. Odd roots can have negative numbers, but not square roots or even roots. And logarithms, which we'll see in section 2.5 and 2.6, you can't put negative numbers or 0 inside of a logarithm. Okay, so here are 3 functions. X squared plus 2x minus 5, x plus 2 over x squared plus 5x plus 6, and y equals 18 minus 12x inside of a square root. So what are the domains for these functions? Well, look at this function. Is it a fraction? Nope. Is there a square root involved? Nope. Is there a logarithm involved? Nope. Well, it doesn't match any of the 3 exceptions, so the domain must be all reals. Whatever number you want for x, you can plug it in there and calculate out a particular y. It'll tell you, give it x equals 3, and you get 9 plus 6, which is 15, minus 10, and that's minus 5, and that's 10. Right? So you plug in your x value, you get out a y value. And exactly one y value. It is a function. What about b? Well, this is a fraction. Right? It's got a denominator. So what does that tell me? Denominator, rule 1 above, can't be 0. So what are the bad numbers here? Well, my denominator, denom, I won't write out the whole thing, we'll just write denom, is x squared plus 5x plus 6. And we know how to factor that now. What makes this 0? Well, by factoring it, we can answer that. X equals minus 2, x equals minus 3, right? That factor and that factor. So what's the domain here for B? All x except x equals minus 2, x equals minus 3. So we can see this work, right? What's f of, say, 1? So what am I doing there when I say f of 1 written like that? Well, that means I'm plugging in x equals 1 into the formula, which is right up here. X plus 2 over x squared plus 5x plus 6. So if you plug in x equals 1, what do you get? You get 1 plus 2 over 1 squared plus 5 times 1 plus 6. Right? And what's that equal to? 3 over 11, 12, 1/4. Right? And that is a y value. Right? So if x is 1, then y is 1/4. Plugging in x equals 1, you don't run into any problems. On the other hand, if we tried to calculate f of minus 2, what do you get? Well, let's actually try f of minus 3. What do you get? You get minus 3 plus 2 over minus 3 squared plus 5 times minus 3 plus 6. And what's that? Well, I get a minus 1 in the top. And then on the bottom I get 9 minus 15 plus 6. 6 plus 9 is 15. I get 0. No divide by 0. So minus 3 is a bad number. You can't plug minus 3 into this function because you get a 0 in the denominator. And we know that because we set the denominator equal to 0, solved it, and we got minus 2 and minus 3. So the domain is all the x's except those x's that make the denominator, in this case x squared plus 5x plus 6, equal to 0. And finally, the last one, y equals square root of 8 minus 12x. What do we need for the thing inside? This has to be greater than or equal to 0. That's a horribly drawn brace. Right? Whatever's inside of the square root has to be greater than or equal to 0. You can't take the square root of a negative number. So I need 8 minus 12x to be greater than or equal to 0. 8 greater than 12x. Or finally, if you divide both sides by 12 and simplify, you get 2/3. So any number bigger than 2/3, you can plug into that and it'll work out because you get a positive number. So if you plug in x equals, any number less than 2/3. So if you plug in x equals 0, you'll get square root of 8. But if you plug in x equals 1 into this, you'll get 8 minus 12. That's minus 4. That's the square root. Some people like interval notation. I don't. I like to know what letter I'm dealing with. This is my domain because there's an x in it. X is domain, y is range. Some people like the interval notation, but it doesn't tell me whether this is the domain or the range. So I'd like to have the x there. So the domain for a square root, then you take the thing inside the square root, set it greater than or equal to 0, and solve for x, and that'll give you an inequality, and that'll tell you what the domain is. Okay. As we continue on, we come to some long-winded problems, 87 through 92. So it's like 87, 89, and 91 are the same problem, just sort of 3 parts of it. So the company is a linear price demand function, right? And this is, we saw this back in section 1, 2, I think. X is a quantity, P is the price. So if they put that much X out onto the market, they get a price P that is 100 minus 4X. And the research shows this holds well for X is between 1 and 20. If X is less than 1, you're not supplying very much, and this model might not work very well. If X is bigger than 20, then the price is going to drop down close to 0, and so again, that model might not work very well. So when you're doing research, you'll find domains are sort of restrictions where your research applies. It might not apply outside of that range. Okay, so X is the amount of stuff they sell, P is the price they can get for it. And the same company has a linear cost function, C of X equals 100 plus 20X, right? So there's our fixed cost, there's our variable cost, and again, for X is between 1 and 20. So various questions that arise. We know the price, the cost, what's the revenue function, how much money is they coming in? Graph the revenue and cost functions and find the break-even points. What's the profit function? How much profit do they make if this is their price and this is their cost? Graph the profit function and find, find values of X for which profit is 0 and for which profit is a maximum. So, what is the revenue function? Well, revenue is the price you sell things at times the number of things you sell. If I sell coffee for $5 a cup and I sell 10 cups, then it's $50 that I make in revenue, 5 times 10. So price times quantity, that equals revenue. So my revenue function here, which we'll abbreviate R, is 100 minus 4X times X, or 100X minus 4X squared if you distribute with the X. And if you've got a graphing calculator, you can graph the revenue, this parabola, right? It's a minus X squared, minus 4X squared, so it opens down. That's my revenue, right? Revenue reaches a maximum in here somewhere, right? And it looks like around 12.5. If you're not selling very much, right, then X is very small, and so your revenue is very small. If you sell too much, if you flood the market, then you drive the price down, right? And so then your revenue drops again. So somewhere in between, right? The price is high and the quantity is high, then you can actually get your maximum revenue. This is the cost function, right? C equals 100 plus 20x. Slope of 20, y-intercept 100, right? So there's my y-intercept. It's down here, slope of 20. Note that this graph doesn't actually go over to 0, right? So 0 is over here a little bit. It's just graphed from 1 to 20 because my domain is from 1 to 20. It doesn't hold outside of that, so we don't include the 0. But it's a line, 100 plus 20x. There's the line. Okay, so this is my revenue, this is my cost. At a particular value, say 10, I have a revenue of 600, I have a cost of 300, right? If R is, say, 20, if the quantity is 20, this is X on this one, and revenue and cost on that. So quantities made, this is all in dollars. If I'm making 20, then my revenue, my cost is around 500, but my revenue is about 400. So I'm actually losing money here, right? And I'm losing money here. So if R is greater than C, wherever the revenue graph is above the cost graph, then making money. Right? And if R is less than C, like here, your revenues are less than your cost, then what are you doing? You're losing money. So as we saw in chapter 1, if revenue equals cost, that's our break-even point. And there's 2 of them. And you can tell where they are on this graph pretty quickly. Right there and right there. Those are my break-even points. And so what does that tell me? If these are the corresponding x values, well, as long as x is between here and here, then you're making money. Right? And that's why one of the reasons why I want to know what the break-even points are. Right? In between the break-even points for this particular model, I'm actually making money. My revenue is above my costs. So what are the break-even points? Well, we can actually find that now because we know what the revenue function is and we know what the cost function is. So revenue equal to cost. This is 100x minus 4x squared equal to 100 plus 20x. It's a quadratic function. How do we solve quadratic functions? Well, we need to get a 0 on one side. So we move all of this stuff over to the right. So 0 equals a plus 4x squared. 100x comes over as a minus, oops, it's a plus 20x. Comes over minus 100x. Minus 100 plus 20 is a minus 80x. And then the 100 stays on that side. What we can do is we can divide through by 4 to simplify my numbers a little bit. And we're left with that. So, you know, I need two numbers that multiply together to give 5, but add together to minus 20. Well, 20 multiply together to 25, that's only 5 and 5. You're not going to get minus 20. So how do we want to solve this? We use a quadratic formula. X equals negative b plus or minus square root of b squared, that's 20 squared, which is 400, minus 4ac, and 4 times 25 is 100, all over 2a. If you grind it out and simplify it a little bit, it should be 10 plus or minus 5 square root of 3. X equals roughly 1.34 and 18.66. Those are my break-even points. Right? And again, 1.34, that's right around there. 18.66, that's right around there. Those are the 2 points where the two graphs cross, where my revenue and cost functions cross. And those are my break-even points. I want to make stuff in between here and here. But how much do I actually want to make? Right? This looks like it'd be the maximum revenue. But what I'm actually interested in maximizing is revenue minus cost, right? This distance. I want to make that as big as I can, right? I want my revenues as big as possible above the cost. So what I'm going to do actually is instead of graphing revenue and cost, what I'm going to graph is profit, which is revenue minus cost. It's the distance from here down to there. And we want to know about profit, the same sorts of questions. What's the profit function? Can we graph it? Find values of x for which the profit is 0 and for which the profit is a maximum. And there's the graph of the profit function. Profit, that equals revenue minus cost. And so in this case, P is, well, again, revenue is, what do I put my revenue function? 100 minus 4x squared minus the cost, which is 100 plus 20x. And then if we simplify that, remember to distribute the minus to both sides, we get profit equals minus 4x squared plus 80x minus 100. It's this parabola. There's our profit function. So, a couple of questions there. When is profit equal to 0? Well, you can look at this on the graph. We know how to read a graph. What's the x that makes p equal to 0? Well, you go to the graph and you say, okay, output is 0, happens there and there. Right? And can we solve for that? Sure. Profit equals 0. What does that mean? minus 4x squared plus 80x minus 100 equals 0. Solve for x. But this, profit equals 0, is, surprise, well, hopefully not a surprise, that's the same equation as this, right? Revenue equals cost. It's a break-even point. So revenue equals cost is when your revenues are equal to your cost. That means you got no profit. Right? So we actually already know what this is. So we know what those are. They're 1 point something here and 18.66. So in here, let's say flip with space, between break-even points, you're making a profit. Outside of that, if you go out here, your profit is actually negative, right? Which means you're losing money. So what is the maximum profit, right? That's what we'll be looking for. Well, maximum profit is about here. Turns out, and we will see how to do this in section 2.3, right. So see section 2.3, we'll actually go through that. If you have a calculator, of course, you can graph this and you can read this off a little bit. Right, but that's the top of the graph. That's the maximum. The highest profit you can get is 300, and that occurs at x equals 10. Note that that's not quite the same thing as where the maximum revenue is. Oops. Maximum revenue is a little bit more than 10. It is actually closer to 12 than 10. Right? The maximum profit actually is here. Right? That's where this line is the longest. Is when x equals 10. So this is actually slightly less profit than that. Okay. So finding the maximum, this point for a parabola is called the vertex, and we want to be able to find that because that'll tell us what the maximum profit is. But